How's it going, everyone? Well, that's a good question, Gabriel. I'm still working that, to be honest. Now, last time I believe we finished section 1.4. Um, there's a chance that today we wrap up both sections 2.2 and 2.4. And that would finish our material for the first test. So, what we would do in that scenario is on Monday next week we'll review, and then on Wednesday next week well, technically the test would be scheduled Wednesday, um, but then I'll give you a window from from basically Monday night until Sunday night, during which you could take the exam. Okay. Now, that is assuming that we finish both sections in Chapter 2 today, which we might. I don't know. We'll see how it goes. Mm-hmm. Before we get started, are there any questions on um, the homework for section 1.4? Hmm. Sure. 25. Okay, we have 3 plus the square root of 3x plus 1 equals x. Okay. Now, solving a problem with a square root in it, step one is we want to make sure we get the square root by itself. So we'll take our 3 and subtract that over to the right. Okay. So from here, we can go ahead and square both sides to get rid of the square root. That gives us 3x plus 1 equals x minus 3 in parentheses squared. Now if we square that x minus 3, we get x squared minus 6x plus 9. And because we have x squared on the problem, we want to move everything to one side so it's equal to 0. And so let's go ahead and take our 3x and our 1 and subtract them over to the right. Right. So now we have x squared minus 9x plus 8. Now at this point we could factor and solve this because this is a factorable expression, and that will give us 2 answers. But if we use the quadratic formula, we'll write that up here. So we start with negative b, which will be 9, and then b squared, which is 81, minus 4 times a times c, and everything divided by 2a. So under the radical, we end up with 81 minus 32. And I believe that comes out to be 49. And so from here, we know the square root of 49 is 7. So we get 9 plus or minus 7 over 2. Now we can split that up into two solutions. One is 9 plus 7 over 2, and the other is 9 minus 7 over 2. So we can tell that 9 plus 7 is 16, divided by 2 is 8. 9 minus 7 is 2, divided by 2 is 1. So we have x equals 8 or x equals 1. Now again, with a square root problem such as this one, we want to make sure we plug in our answers and get valid results. So if we start with the x equals 8, we know the right hand side will be 8. 3 times 8 is 24, plus 1 makes 25, and then we have the square root of 25, which is 5, and then 3 plus 5, which is 8. And so that actually checks out. For x equals 1, sorry, drop my pen. There we go. For x equals 1, we know the right hand side will be 1. 3 times 1 is 3, plus 1 makes 4. Square root of 4 is 1, or 2, sorry, not 1. And then 3 and 2 is 5, and so we end up with 5 equals 1, which is simply not true. So we can rule out x equals 1. So the only solution here is x equals 8. Okay, not a problem. Yeah, it's the kind of thing you know you should be able to work both ways, but it's frustrating when it doesn't happen. Yeah. 61, 79, and 83. Oh yeah, the quadratic like equations. Okay, 61. We have x to the 1/2 minus 3x to the 1/4 plus 2 is equal to 0. That's a 1/2, sorry. All right. Now, we know we can factor this, and we have to kind of think, okay, what multiplies to negative 3 and adds to positive 2? And our conclusion there is that it's negative 2 and negative 1. Because negative 2 plus, nope, I messed it up, I'm sorry. Positive 3 and negative 1. 3 times negative 1 is negative 3, and then 3 plus negative 1 is positive 2. Okay? So we know what the numbers should do here. The question is what's going on with the variables, because we have x to the 1/2, x to the 1/4, and then the constant. So we set up our factorization. We know one of them is going to be plus 3 and the other is minus 1. And so the question is, how do we split up the x to the 1/2 into these two pieces? Well, there's two ways that we talked about how we could establish what goes here and here. The first way is that we just look at whatever this middle term is, x to the 1/4. And the second way is that we just divide this exponent by 2. 1/2 divided by 2 is still 1/4. So it's actually 1/4 either way that we look at it. And that's the point, is that whichever way we look at it, we should end up with the same term in both of those places. Now, we can go ahead and go through and solve these. So, x to the 1/4 plus 3 equals 0. So x to the 1/4 equals negative 3. And x to the 1/4 equals 1. So the last thing we need to do is to figure out, how does x to the 1/4, how does that affect this answer? Now, when we have something raised to the 1/4 power, what that actually means is that we're taking x and we're applying the 4th root. So we can say this is the 4th root of x equals negative 3, and the 4th root of x is equal to 1. I made a mistake at the very beginning, and I attempted to correct it, and I did not. adds to negative 3 and multiplies to positive 2. So I was actually right when I wrote down negative 2 and negative 1, but I looked at what I had written above it and I couldn't resolve those two things. Anyway, yeah, so this is a negative 2. That's my bad. This is a positive 2. This is positive 2. Anyway, sorry about that. So, we have the fourth root of x equals 2, and the fourth root of x equals 1. And then we'll just raise both sides to the fourth power. We'll get our two results. Okay. Does that make sense? Let's see. Yeah, and these will be factorable. That's the main thing. They're factorable, but we have to figure out, what these exponents are going to be when we split them up. Yeah. So that's so we still have 79 and 83. Now, actually, I don't think I talked about 79 and 83 on how to do those. I think I assigned them in anticipation of completing those problems, how to do those problems today. But I went ahead and gave you the full assignment for that section. So that's probably part of why you're not sure what's going on with 83 in particular, but also potentially 79. So what I'll do is I'll start with problems similar to those two today, and we'll go from there. Okay. Were there other questions? Yeah, I went ahead and assigned those last two in case some people wanted to go ahead and work them and try them out, but yeah, I hadn't talked about them just yet. So we'll do similar problems to 79 and 83 today, and then you should be able to look at them and be fine, hopefully. Okay. Yeah, so let's look at those before we go much further. Let's see. So to begin with, I want to look at number 80 on page 118. And the idea here is that we want to look at a few what we call cubic equations, not quadratic, but cubic because they have x to the third power. And so, because of this, it does potentially change how we solve them. Now, this first example is not a drastic change because hopefully the first thing that we notice with this equation is that all of our terms have at least an x in them. So we start off having a common factor of x. We can factor that out. So we take out an x from each term. That leaves x squared plus 6x minus 7 in parentheses. And then from there we want two terms that multiply to negative 7 and add to positive 6, and that would be -7 and -1. Good. So we can then factor, so we have x already, x plus 7 and x minus 1. Now one thing that we had said before, earlier in this chapter, is that if we have an x factored out, and then that basically gives us x equals 0 as one of our solutions. We can then get the other two from our factorization, which is x equals -7 and x equals 1. And so that right there is our three solutions to this problem. Okay. So really this question, even though it's cubic, because there's no constant term, it is considered a factorable equation because we can just take out a common factor, which leaves us with just a normal quadratic to work with, and we can solve the quadratic a bunch of different ways that we've learned already. So that's 80. Now the other one I want to look at, which will be probably 82 or 84 or both. Let's look at 82. So we have x cubed plus 4x squared minus x minus 4 is equal to 0. Okay. And we can tell this one's different from the last one because we have that minus 4 at the end, so there's no common term to take out. If we're going to factor out a common factor, all four of these terms would have to have that term in common. And that's not the case here. So that means we're going to have to require some sort of different approach. So here we're working on what's called factoring by grouping, which is especially something we want to consider applying when we have four terms like we have here. Okay, and what we do is we actually group together the terms x cubed plus 4x squared. We group them by putting them in parentheses, plus and then negative x minus 4 equals 0. By putting them into groups, we set up a situation where we potentially have a commonality between the pair of terms now that wasn't there between all four terms together. What do x cubed and 4x squared have in common that we could factor out? X squared. So we can take an x squared out from both terms, and that leaves x plus 4. So both of them have at least x to the second power. Now, negative x minus 4, we look at those, there's really no number in common, and they don't have any x's in common. What they do have, though, is a minus in common, so let's factor out a negative. And we can think of it as a negative 1 if we like. Okay. So by taking out the negative, that turns both of these into positives inside the parentheses. Just divide by a negative makes positive, divide by a negative makes positive. So at this point, what you'll notice is that, okay, we factored out a term from each group, and what's left inside is an identical factor. Both of them have x plus 4 left over. And this is key to the factoring by grouping process. As long as this has the same identical term left in parentheses, we can factor further to the next step. Because if we think of this as one object, and we think of this as a second object, both of these have an x plus 4 in parentheses in common. So you factor out the x plus 4, and what's going to be left from the other two parts, or from the other parts there? So we have this, we took out the x plus 4 that was in parentheses from each of these terms, and what's left over? X squared minus 1. And that right there is the key step in factoring by grouping, is that we have a binomial that's in common that we factor out, and we're left with whatever was in front of the first binomial and whatever was left in front of the second binomial. Those end up getting grouped together. So an x squared and a minus 1 that we just put together, basically. Okay? No? Yeah. I think everyone's okay up to here. It's just this step is the one that's really confounding. So we think about it like this. What if we had x squared times y minus 1 times y equals 0? And we said, okay, we can, since the y is in common, we can factor out y and leave x squared minus 1 as the other factor. Okay? So the concept here is that instead of a single variable like y, we actually have a binomial in parentheses x plus 4 that is actually being treated as a common factor. Okay? we have x squared times a term minus 1 times a term, and because those are the same exact terms, we can factor a binomial out from each of these parts of this expression. So taking this x plus 4 out, we end up with x squared and then minus 1 left over. And we can think of it, if we wanted to reverse that process. Good. And we can think of it, if we want to reverse that process, we can take x plus 4 times x squared and x plus 4 times negative 1 and go back and get that same expression. Okay. Now, at this stage, having successfully done our factorization, we still need to factor this expression one step further. And this is what we see a lot of the time in these what we call factoring by grouping problems, is that we'll get a normal binomial and then we'll get one that's quadratic, but it's also factorable, which means we can split it into a difference of squares, or we can just solve it with the square root method, whichever way that we prefer. So we know that we're going to get x equals negative 4. And then here, if we have x squared minus 1 equals 0, we can add the 1 over and then take the square root of both sides. And so we get x equals negative 4, x equals 1, and x equals negative 1 as our three solutions. Okay. Now, we didn't have to, solve this that same way. We could have factored x squared minus 1. We said it was x minus 1 times x plus 1, and we'd arrive at the same answers, ultimately. So, we do have some choices there as far as how we would like to work that. I think from what I've seen from other students or from previous students is that the majority of them prefer using the square root method when possible, so that's how I tend to teach that. Yeah, we can do one more. Yeah, so we'll go ahead and do 84, which should be very similar. Okay, so we said this is factoring by grouping, and we'll start off the same way. So we'll go ahead and group our pairs of terms together. Now again, what really signifies us to use factoring by grouping is that we have 4 terms in our equation, and we have x cubed being first, so it's we don't really have a term for it having 4 terms, it's just a polynomial, but it's a 4-term polynomial, and it's a cubic polynomial as well. That's another factor there. And so in this scenario, as long as there's no common factor between the 4 terms, we should just move forward excuse me, with the factoring by grouping. So we put them into pairs, and again, the way that we pair them up is always the first 2 terms and the last 2 terms. Once they're they're in the normal order descending from highest exponent down to lowest. So we get the first two together and then the second two together. What common factor can we take out of these two terms? Well, it's actually just like the last problem where, we have x cubed and we have x squared, so we know that we can take x squared out of both. Taking out x squared leaves x minus 3 in parentheses. And then minus x plus 3. Now that we've finished the first one, part of what we should be looking at trying to do here is to make whatever is left in these parentheses match what's in this parentheses. So if we have minus x plus 3, that's opposite what's here. Let's factor out a minus 1 once again and make that an x minus 3. Now that we've seen one of these problems, we can start looking at some of the finer details, like what are we actually trying to accomplish? Well, we want these two expressions to be identical. Okay, and that's why we need to, even though there's no common factor here, sometimes there is, sometimes there isn't. But even though there's no common factor here, we still want to take out that negative to make sure these interior expressions match each other. Does x minus 3 minus x minus 3 equal 0? Yes, that's correct. However, we cannot subtract those directly because of the factors that exist in front of them. I mean, technically, this expression here is x cubed minus 3x squared, but we've changed how it looks. This expression is negative x plus 3, but we've changed how it looks. So with that product attached to it, that's where it prevents us from actually subtracting those terms. Okay. Now, each of these parts or each of these halves of the problem have a similar binomial, x minus 3 in parentheses, has those terms in common. So what is our factorization on our last step of the factoring? X minus 3 and then x squared minus 1. Good. Yeah. Now we can write them in any order. I tend to put the x minus 3 first because that's actually being factored from each of these terms out to here. And then we're putting x squared and minus 1 together to create the other factor. So at this point, it's actually very similar to what we saw last time because we got a normal binomial that we can immediately see that x equals 3 is our solution there. And then with x squared equals 1, what two solutions is that going to give us? One and negative 1. Yeah. And again, we know that's because we can take the square root of both sides and get plus or minus the square root of 1, which is just 1 or negative 1 on the right. Okay, is that you'll feel a little bit better with that? So in addition to that, you'll have 83 on your homework still to practice, so I think that'll be a good gauge of how well you did get that, between 82 and 83. Yes, or sorry, 82 and 84. Yeah, you could do 83, which I assigned, and if you want to, you could try 85 also, and 81. And those, at least in the physical copy, they have the answers in the back of the book. I assume in the e-book you can still go to the appendix and get the odd answers there also. So I assigned 83 for homework, but if you wanted to also try 81 and 85, those are going to be very similar. As far as the process is being used, you'll get some different answers for those. Okay. Yeah, usually I don't assign a whole lot of homework, but the good thing there is if you do want to find more problems similar to what I've assigned, they're usually pretty close to the problems that we already are doing. But if you want to be sure, feel free to email me and I can specifically point out which ones would be relevant. What is this lesson called? Factoring by grouping. This is last part of section 1.4. Okay. So yeah, 83 is on the homework, but if you want, you could also try 81 and 85 and get some more practice with this topic. Okay. So from there, let's go on to section 2.2. In the first two chapters, we kind of skip around, but when we get to like chapter 3, 4, and 5, we do, well, not 4, we do all of 3, part of 4, all of 5, most of 6, and parts thereafter. So it's kind of a mix what we do, but yeah, our first test will be over chapters 1 and 2, but specifically the sections and the material that we covered here in class. Anyway, so 2.2 is next. And this is on intercepts. Now, the title of the section is actually on graphing equations in two variables, intercepts and symmetry. I want us to hold off on the graphing until we get to chapter 3, where we do it in a lot more detail. So we'll just worry about it a little bit more later. And then the symmetry, I don't want us to really concern ourselves with. Um, it it's a little bit confusing, to be honest, but more than that, it's not what I would call essential. So um, even my calculus students, where they can use symmetry, it's actually not a huge time saver because you can just work the problem as it is and arrive at the same conclusion. Symmetry is a little bit more important in some problems when you get to more advanced math, but by then I think it'll be alright. So, um, when I say advanced math, I mean like numerical analysis and partial differential equations, which are like junior level math major classes. So, anyway, we're a ways off from that. So the long story short, I just want to focus on intercepts in section 2.2. So it's actually a relatively short lecture for this section. And the idea of an intercept, this is a coordinate or point where a graph crosses or intersects either the x or y axis. Okay. Now, to begin with, we're going to look at this from a graphical standpoint, and we're going to look at it from an equation standpoint. You know, what to do how to find intercepts with the graph, and how to find intercepts if we don't have a graph, we just have the equation instead. So if we have a graph, such as this, we can see, looking at where the graph crosses or intersects the x or y axes. Now, when we identify the x-intercepts specifically are the intercepts that occur on the x-axis. So which coordinates do we have there where it crosses or intersects the axis? Three and negative 3. Yeah, 3 and y is 0. Yeah, 3 comma 0 and negative 3 comma 0. I would prefer that we go ahead and express the intercept in this case as an ordered pair, because that way we know exactly which coordinate we're talking about. But overall, if we just said x was equal to 3 or negative 3, I would understand what you're talking about there. What about the y-intercept? And again, here's our y-axis. Zero, 3. Good. I should have drawn a graph where there weren't all 3s. So figure I probably could have made an extra mark in here, but that's fine. Yeah. I did kind of distinguish whether the graph crosses or intersects. Like these 2 points, I would say the graph is crossing those axes. It crosses the x-axis here at -3, crosses the y-axis here at +3, and then I would say intersects the x-axis at +3 right here. But it doesn't cross because it doesn't go from one side of the axis to the other. Okay. Now, how we distinguish those types of intersects or intercepts, that will become more important later on in, I believe it's chapter 5, where, or maybe 3. Honestly, I don't know. later on this semester, we're going to be graphing these higher order quadratic, or not quadratic, higher order polynomial equations, and it'll be important for us to know the difference about whether a graph crosses or intersects the axis. So, don't worry about it too much right now, though. But I wanted to kind of plant that seed, just so we keep that in mind. So yeah, it's pretty easy to actually identify the intercepts because we can see plainly, especially if the graph is labeled, where we see the marks for the different values on the axes. It's pretty easy to see where those points are located. It's just a matter of expressing it properly, which, again, I would prefer that we use an ordered pair for that because it is an easily recognized position for the location of the intercept. Alright, now the other part of this section is what do we do if we don't have a graph and we actually want to use the intercepts to help sketch the graph, which is something we'll talk about a little bit later. How would we find the intercepts if we only have the equation? For instance, we have x plus 2y equals 8. We want to say, what are the intercepts? Well, this one's not terribly difficult because I chose a linear equation. We'll also look at some quadratic equations. The key, though, and we can go back to our graph to kind of illustrate this. Notice that both of our x-intercepts have a y value of 0. Having a y value of 0 means that the point is neither above nor below the axis, it's right on the axis. And that is actually what makes it an intercept in the first place, is right on the axis. Okay? So y value of 0 is actually how we would find the x-intercept. And in a similar fashion, all the y-intercepts, or if there is more than one, will have an x value of 0. So in order to find an intercept, we set the other variable equal to 0. Let me write that down. Okay, so to find the x-intercept, we set y equals 0, and to find the y-intercept, we set x equals 0. Now, if we set y equal to 0, what's left in our equation? Well, we can see that's just x equals 8. Putting y equals 0 in here, we just get rid of that term entirely, so x is equal to 8. Okay. If we set x equal to 0, that gets rid of our x. What would y equal then? Four. And so our ordered pair would be 0, 4, and that would be our two intercepts here. For a linear equation such as this, if we just graph the two intercepts, then we have basically all that we need to sketch a graph of the line itself. Okay. Quadratics and higher order, polynomial equations and other types of equations will certainly require more than an intercept, but even in those cases is a nice start to establishing where the graph is and where it's going. Okay, let's look at one that's a little bit more involved. Let's say that we have y equals x squared plus 5x plus 6. Now, if we want our x-intercepts, again, we know that we set y equal to 0. So we plug in 0 for the y, and that gives us the equation 0 equals x squared plus 5x plus 6. How are we going to go about factoring that quadratic trinomial? We know that we need two numbers that multiply to 6 and add up to 5. Three and 2, good. And so from there we can solve for x. We get x equals negative 3, x equals negative 2. And if we write those as ordered pairs, then our intercepts are negative 3 comma 0 and negative 2 comma 0. Okay. And then for our y-intercept, again, we know that we set x equal to 0, and that's actually much easier here, because if we plug in x equals 0, we get rid of most of the equation, and we just see that, okay, 0 squared plus 5 times 0 plus 6, that just leaves us with y equals 6 left over. Okay. So we have the intercept 0 comma 6. Now, unfortunately, if we tried to graph these, it wouldn't give us a great idea of the graph of this particular equation. And this is a topic we'll look at in more detail, I believe, in chapter 4. We look at graphing quadratics specifically. We also need the vertex, because we don't know if these intercepts represent the key values in the equation. We just know these are the points where it crosses either the x or the y-axis. The 3 and the 2 here, Madison. Well, again, we're thinking about, and let me kind of put an aside in here. We need two numbers that multiply to 6 and add to 5. And that's what these two numbers represent. Now, there's different ways to get a product of 6, but only one of those also adds up to 5, and that's our 3 and our 2. 3 times 2 is 6, 3 plus 2 is 5. Okay. All right. Now we can have some stranger problems here. Um, Basically, these will be nonlinear, or not nonlinear. Well, they are nonlinear, but they aren't actually functions. They're just equations. So we could say x squared plus 4y squared is equal to 16. And the graph of this is actually called an ellipse. And this is one where graphing the intercepts actually gives us a very nice view of the graph that results from this. Now again, starting with their x-intercepts, we know that we plug in y equals 0. If we get rid of the y's by plugging in 0, that just leaves us x squared equals 16. And what would x equal then? Four and negative 4. Good. Yeah, in reality, we're basically just taking the square root on both sides here. Square root of x squared is x. Square root of 16, we'll put plus or minus square root of 16. So x is 4 and negative 4, so we get the ordered pairs 4 comma 0 and negative 4 comma 0. And we can repeat that same process with the y-intercepts. This time we let x equal 0, and if x is 0, then it just leaves 4y squared minus 16, or equals 16, sorry. Now before we apply the square root to both sides here, what else should we do first? Yeah, we'll need to divide by 4 first in order to get the y squared by itself. So the square term has to be alone before we take the square root on both sides. It's actually a lot like how if we have a square root in the equation, we get that by itself before we square both sides. It works both ways. So we'll divide everything by 4. So that gives us y squared equals 4. Now we can take the square root. And so we get y equals positive 2 or negative 2, so it's 2 comma 0 and negative 2. Nope, no it's not, I'm sorry. 0 comma negative, or 0 comma 2, and then 0 comma negative 2. There we go. Again, we want to make sure we get them in the right order. The y-intercept always is 0 first, and the x-intercept is always 0 second. Okay. Now, as I said, this is also a good way to sketch this particular type of graph, which I called an ellipse. We're not actually going to study how to graph an ellipse this semester, which is fine. But, if we wanted to, we would, x equals 4, x equals negative 4. Y equals 2 and y equals negative 2. And then we can just draw the resulting graph there. Somewhat poorly on this edge, but that's fine. Yes, four answers in this case. And depending on the graph itself, it could have multiple answers. Everything we've worked on so far, like working with quadratic equations, we tend to have just the two x-intercepts and the one y-intercept, but this is still considered quadratic, I guess, but both variables have squares now, which actually increases the number of intercepts. Okay. Were there other questions on these? All right. Let's see. We can talk a little bit about circles, but I think we'll save that section for next time. Yeah. So, section 2.4 is on circles. And we want to be able to talk about both the equations and the graphs of circles and basically show how they're connected. Now, we just looked at that ellipse problem. We didn't have to graph that ellipse, so don't worry about needing to graph those things. But I mentioned that the intercepts in that case were actually a great tool for sketching those graphs. And that's what when I taught Calculus 3, I'd always have my students graph their ellipses that way, using the intercepts, because it just worked out so much easier. And to be honest, our equations were not that difficult. We just had there were actually equations in 3 dimensions, but we were looking at it from 2-dimensional cross sections. Anyway, it's not here nor there. But looking at circles are actually very similar to ellipses. Let me just give you an example. If we have just x squared plus y squared equals 9, for instance, this is an equation of a circle. Now, what are the x-intercepts for the circle? If we set y equal to 0, we get rid of the y. We just have x squared equals 9. And so x would equal 3 and negative 3. Yeah. So we get two intercepts, 3 comma 0 and negative 3 comma 0. And for our y-intercepts, if we set x to 0 and we solve y squared equals 9, again, we get the same combination of numbers. So we get y equals 3 and y equals negative 3, which means our intercepts are 0, 3, and then 0, negative 3. So if we were to sketch those 4 coordinates, 3 up, 3 to the right, 3 down, and 3 left. And then we can just draw the curve connecting those. And we get something that's more or less a circle. That's about as good as I can draw them, so that's good. Yeah, and so that would be the graph of a circle. Now, we can already see the difference between a circle and an ellipse, because if we look at our ellipse again, we notice that it was actually wider than it was tall. And that doesn't make a circle. A circle has to be equal in height and width, basically. So if we look at those two equations, where for the circle we had x squared plus y squared equals 9, and for the ellipse we had x squared plus 4y squared equals 16, what is the contributing factor in this ellipse that makes it not circular? Maybe maybe I didn't word that correctly. But yeah, the 4. Good. At least someone deciphered what I said. Yeah, if we didn't have this 4 here, then we would actually have identical intercepts for both x and y, because we would say x squared equals 16 and then y squared equals 16, and that would give us our 4 intercepts. And it'd be a perfect circle with radius 4, instead of having a radius 2 one direction and a radius of 4 the other direction. And so that's the difference right there between an equation for a circle and an equation for an ellipse, is that we have to have the same coefficient on x and y squared for this to be a proper circle. Okay. So each of these graphs, though, the reason that we're able to sketch them using the intercepts is because they're both centered at the origin. So the issue is, what if we have a circle that's not centered at the origin? For example, if we end up with a circle such as this, maybe our center is located right here at negative 2, 1, and we have a radius of 3. And we end up with this circle, so to speak. Okay. And we look at where it crosses the x and the y axes, and it looks like it's not an exact number. It's not a whole number value by any means. It's somewhere between 2 and 3 on the y-axis, and also it's probably not exactly negative 1, even though it appears to cross there. That's just my drawing. But none of these intercepts in this case would actually be a whole number. Okay? And I can write out the formula for this, but we're running out of time, so I don't want to dive into this just yet. We'll probably talk about this starting next time. But when our circle is not centered at the origin, our intercepts are going to be kind of off wherever they want to be. They're not going to be whole number values by and large, so there's no way for us to depend on that as a method for graphing. Now, the other question is, well, how do we know how to sketch the circle? How do we graph the circle then? Well, you might have noticed when I sketched this particular graph, I located the center first, which is negative 2, 1, and I made a mark there. And then I said, let's use a radius of 3. So from the center, I went up 3, right 3, down 3, and left 3. Okay? So the definition of the radius is the distance from the center to any edge of the circle. Okay? So all of these points are a distance of 3 from the center point. But it's only easiest to work with in kind of our cardinal directions, north, east, south, west. So we just go up 3, right 3, down 3, and left 3 from that center, and we're able to find the points that are on the edge of the circle. There are other points, of course, but those are the ones that are most easily located. So it turned out to be able to graph a circle or find the location of a circle in the xy plane, that's the two things that we need: the location of the center and the radius. And that's something that we'll emphasize in today's Wednesday, so next Monday's lecture. That's what we'll emphasize a little bit more, as far as how do we locate the center and the radius of the circle, and then we can use that to create the sketch accordingly. Alright, let me just pick out some problems from section 2.2 for us to look at today. And again, I only want us to find intercepts, so don't worry about finding symmetry or anything else that these problems ask. So on page 166, go ahead and look at number I got 41, 43, 47, and if we want to be specific, just part A on those problems. And then also look at 57, 61, and 63. And again, just look for intercepts there. Okay. So, what I'll do is I'll go ahead and post the review on Canvas for chapters 1 and 2. It probably won't be until after Wednesday's lecture next week that we'll be able to take the test. Yeah. So what I'll do is, we'll probably spend part of Monday's class going over the review problems, any questions on the review, and then also in Wednesday's class next week. And then you'll have time to take the test anytime, basically from Monday next week until Monday the following week. And I'll probably go like midnight to midnight just to make it easier. I find that I really confused my students last semester when I set deadlines that were not at midnight, so I'll go ahead and stick to that. But that means if you need to, you can just take your test during Monday's class the following week. We'll talk about it more next week, since we'll have time during when we're reviewing to kind of talk about the format of the test and how questions are going to be asked and everything. So don't worry about it too much right now. I'm going to go ahead and post the review in Canvas as part of an announcement. Yeah, so just worry about working on homework, and if you want to start the review, you can. If you want to wait a little bit, you can also do that. It's just up to y'all. But yes, so if you go into the ebook on Pearson, you should be able to find the same page and the same problems. Yeah. I didn't set it up as a formal assignment inside Pearson, so you actually just have to go to your ebook inside Pearson or eText or whatever they call it, and get it from there, and then you can just read it or whatever. Yeah, and when we do the review, I'll actually post a video that has all of the answers worked out already, basically. So, you'll be able to watch that, and that should help you out if you do have questions on those problems. But I do want to make sure that y'all have a chance to work them first before I show you exactly how to work them, because I think that's an important aspect to the learning process, is being able to, even if we do struggle a little bit, that's part of the process. Okay, so it's okay if you have questions, you get stuck on some things. That's is part of learning, is trying to work through those roadblocks. So, but also, I'm not going to leave you without like a map. So anyway, so y'all take care. Have a good rest of the week. We only had one class this week because of the holiday, which is actually okay with me. I hope probably okay with y'all too, I imagine. But yeah, y'all have a good weekend, and I'll talk to y'all Monday. Bye. Oh yeah, exactly, August. It's nice to know, that you've gotten the correct answer. So that'll definitely be available at some point prior to the test. Yeah. Oh, it's all good, Brock. Don't worry about it.